Cool. I think we are recording. Um, so as I always like to start this with a little bit of note taking. What do we know about hash tables? Anyone just unmute yourself and jump in.
They have constant time lookup.
Okay. Constant time lookup. Constant time lookup by what?
By key.
Mm-hmm. Constant time, or in other words, of no, that's not constant time. Of one lookup by key. Okay. Anything else?
Leo, for
Yep.
sets, aren't those also the containers for those sets? Like wouldn't that also be sort of considered like a hash? Those don't directly have key value pairings though, right?
That's right.
Yeah, so how would that differ? Or like how that's why I was like sort of like I wanted to say like something to do with key value pairing, but I thought about sets and I got confused. So
Yeah. It's funny that you asked that because I was thinking about that recently, and I don't feel like I have a good answer. But the way in which it works is the way that I think it works is in a set. When you add something to a set, you don't have a key.
mhm.
Generally, in the object, what gets hashed, and we're going to see this, is the key. But a set doesn't have a key.
Right.
So I think when an element is added to a set, is the entire element itself that gets hashed,
Right.
and that is what gets used. Um,
That makes sense.
but a set, and I'm not sure exactly about the specifics of how it could be done, the hashing of the element itself.
Yeah.
Um, but I think a set under the hood will still need we'll still need a hashing function that
Yeah.
does that for you. That then takes in the element and derives a hash from it. That ends up being an index in an array.
Yeah.
Mhm.
Definitely. All right.
Yeah.
Thanks.
Okay. What other things do we know about hashes, hash tables? I mean, anything else?
I'm like looking through my notes. I'm forgetting something.
Or think about comparing hash tables to other data structure, compared to an array, for example.
Oh, they are. I I want to. I keep on feeling like they're not officially ordered.
That's exactly right. They are on order.
Like not zero indexed or anything like that, right?
Right.
Yeah.
Mm-hmm. They're right. They're on order, so you cannot rely on them for this element is first, this element is second, this element is third. Yeah, on order. Uh, Anything else?
They have key value pairs.
They have key value pairs, and I would like to complement that by saying ultimately a hash table is a collection of key value pairs. Okay.
Leo,
Yeah.
question. So you know how like arrays, in terms of like space complexity, like they have like a fixed space, sort of like in like the amount of elements it can take in. Do hashes fall in any sort of those like limitations, or no? Like, can you put as many key value pairings in a hash as you want, or do they like stop at some fixed point or something? Because I know that like you don't have to do a thing where you would create like a new class of like a hash or something with like a size. So like does that ever come into play at any point or?
So the thing is, like, because we code in JavaScript, and those a lot of those things were already sort of thought out for us, and we're gonna see that actually the um, the way that the hash table is implemented under the hood is with an array, and that's true for all hash tables. And if you think about it, that should make sense with this. Like, we know that indexing an element by or getting an element from an array by its index is a constant time operation. It turns out that under the hood, that's the same mechanism how a hash table is able to do the same thing, but now by key. So in terms of the size that you mentioned, Marvin, um, since the underlying implementation uses an array, and arrays by default are in JavaScript are already dynamic arrays or resizing arrays, then we don't run into any of those limitations. There, we could put those constraints ourselves if we wanted to say, when you create a hash table, then you have to specify how many elements do you want to put in, or what is the size that you ultimately want. But yeah, for the most part, we don't limit the size there.
Okay.
And I guess also I should say that so you see how here I put hash table / objects, because they're the same thing. The way that we're gonna implement a hash table here is more for is more of a thought exercise rather than a practical thing you will do. Like, you wouldn't implement your own hash table because the hashing part is a complicated part that we should get right. And here, the hashing that we're going to do is a very simple hashing that is not the best hashing you could do. And this is more for, like, sort of looking under the hood, really.
Like conceptually, sort of, right? Like
yes.
a conceptual thing. Okay, cool.
Which is always something that I struggle with a little bit on DSA, and where a lot of things are like that, very conceptual and hard to put into practice. Like, like stuff like, we ask you to master trees and be able to traverse a tree and be able to build a tree, but the likelihood of you having to do that in the actual job is like 1%. So yeah, I think the way that I later on myself as a fellow started to look at that is that is simply the bar that the industry has set, and I have to meet that bar if I want to, do this. And then from time to time, things start to just attract my own curiosity, and I learn a bit more about it. Cool. So a collection of key value pairs, they're on order. Yeah, I think yeah. Anything
Keys
else?
are keys unique?
Oh, that's a good one. Yes. Keys are unique. That's a very good point. You can have duplicate values, but you can only have unique keys. Let me see. I remember when I was a fellow, spreadsheets. No. I remember I had done this spreadsheet, which was recommended to me by a. Actually, I think I wanna find it because I think it will be a good resource. I had done this spreadsheet where I compare all the data structures to each other, which I think is a really good exercise. And I want to show you what that looks like. Oh, here it is. Data structure study guide. So
That's cool.
this is something I recommend everyone to do. If, like, having all the data structures here and then pros, cons, the time that it takes for create, insert, find search. I could share this. I could share this doc. I could also share a template with all of them.
Please do.
Um,
That is cool.
Yeah.
so here, let's do pros, constant lookup time, as we said on any key. Cons, no guaranteed setups on order, like what we talked. Oh, this is something that we can touch on. Inefficient if many collisions happen. We're gonna learn what that is, what collision is, and cause keys must be unique. I guess that's like a con, or it could also be a benefit. It depends on how we look at it. This is something that we already talked about. Inserting, adding of one. Even if there was a collision, because adding to a subsequent linked list could take one as well. We're gonna hopefully by the end we get a sense of what this means and why are we talking about linked lists in a hash table. Read lookup. Oh, this is an interesting. We'll talk about it. Constant time if there's no collisions. Linear time where or O of n, where n is the number of elements that had mapped to that same index or that had collided, and we're gonna talk about that and why that could be. Find search. So if we want to find a value, we'll need to look at all the keys. So that will be O of n, where n is the number of key value pairs. We do know, and we do not know that the key that contains what we're looking for. Let me think about this. On rare cases, it might be O of n m if collisions are common, where n is the number of unique keys and m is the number of elements that are already mapped to a given hash. Hopefully, this will have make a little bit more sense at the end. Update edit, that's constant time. Removal, constant time as well, or O of n if there's a lot of collisions happening. But I think we covered most of it. Okay, cool. Any questions on any of that before we jump in?
No, I'm just interested to know what the collisions are. I think that's like a concept that I'm not really too like familiar with.
Cool. Yep. Yeah.
Is new map? That's a hash map, right? Using
That's a hash
like
map.
in some. Yeah, that's what I figured.
What we'll create what we'll create today is more like that hash map than the humble object we use every day on JavaScript. Because what happens is in the object that we create in the regular object that we have in JavaScript, when we do like object that name and then we say equal to Alejo or whatever name, that is inserting, that's already creating a name key in that object, setting the name to Alejo, sort of in a really syntactic sugary way that we don't have to do like hash table that add name Alejo, but that's more the way that we're gonna do it. And also I think at map, if I'm not mistaken, I think a map can use anything as keys. But here we're gonna use the keys that we're gonna have are gonna be all strings. I think a map lets you put other stuff as keys as well, but I'm not sure. That will require some search on that documentation. Okay, so yeah, we're gonna learn what is a hash table, what's a hash function, what is mapping, and what's collation, and how to implement a hash table. So other names for hash tables that you may come across in interviews or in the wild: hash map, dictionary, or associative array. I think I have an issue pronouncing this word, associative. Is that correct?
That's right. Yeah. Associative. Yeah.
Associative array, or dictionary. Those are words that are sometimes known for. I think Python uses that dictionary a lot. They don't say hash tables or hash maps. They say dictionaries. This is one of the most useful, data structures. You can think of anything you have used an object for, and then there is that. So like a problem, or like why hash tables were created was, let's think of it, this example problem. where let's say you're a cashier and customers ask you for the price of certain products often, and then you have a list of products as all of them, um, and in an array. So if they ask you for the price of banana, what would you need to do to find it in this array?
You'd have to iterate through that array and then check the key for banana and like return the value.
That's right. Um, that is exactly right. We'll need to loop over it. So that will be, we'll have to implement a linear search. So that will be all then, which is okay. A way in which we could address that and make it a bit faster is maybe we kept the array in order. There's actually a mistake in this lesson where right now, if somebody asks me for the price of banana, um, and I don't know, I don't know the price they're asking me for it. The mistake in this here is that this array should be sorted in alphabetical order. Right now it's sorted in numerical or the price number. But if it was sorted in alphabetical order, then that means that we could perform web searching algorithm to find banana faster. Uh, I think Douglas, you were unmuted and you muted.
Sorry about that. Binary search. Am I pulling the right word out? Yeah,
That's exactly right. Binary search, because and this will be the example of on like the phone book example, where you're looking for the price of banana and you have this book that has all of them. You can open the book in the middle and see if banana is in one of those pages, and then from there move either to the right or to the left. In this case, you will move to the left, because B is will be likely to be on the first half of the book. So we could do that, and that will give us a log of n. But then the exercise is like, imagine if you had a friend that was just able to memorize the price of any item you told him, and then you just ask him banana, and then he knows the price immediately, $1, and you could ask any price. Well, it turns out that friend is the hash table. The hash table is your friend that knows the price in constant time. So I guess just to reiterate, the problem that hash tables come to solve is looking something up really quickly in constant time. Okay, any thoughts or questions on that? Okay. So let's think about hashing functions. So a hash function, and this is sort of the way that I think about it. When I moved to America, I didn't know what. Now I'm even forgetting it. Hash brown is something you eat, right? Wait, let me Google that, because casserole. Wait, what are hash browns made of?
Potatoes, right?
Potatoes.
Shredded potatoes are like fried.
Okay.
yeah.
But I think of this where, like, I guess you have a potato and then you turn it into something else that is like some other representation of it, and then that is the hash brown. But so hash functions are sort of a similar idea. I don't think that was a very good analogy, where you have some input, some data, and then it produces a hash of that data that is a representation of that. In this case, what we'll do is we're gonna be hashing strings, and we're gonna be hashing those into a number. Hash functions, there are a lot of them. It's like its own area of study in computer science and in especially also cryptography. Um, but a hash function is a function oh, that has to have like two main things. One, it has to be consistent. So for some input, for the same input, it should produce always the exact same output. So if we feed this function apple and we get 4, every time we feed it apple, it should give us 4. Without this, then the hash table won't really work. And it should map different inputs to different values. In this case, to different numbers. Um, if if a hash function is returning the same hash for multiple values, um, then that might mean that it's not a very good hash function, and we're going to have a lot of collisions with it, which we're going to get to talk about. So I feel like I'm missing something here. Let me see. Like in this, in the example of like our bananas and or our grocery or store example. So if we're hashing apple and we get 4, and we hashing orange we get 2, we hash banana we get 7. That's looking like a good hashing function. Even though I guess maybe just looking at 3 examples won't be enough. But if we get that the hash function was giving us 1 for or 2 for orange and strawberry, then maybe that's not a good hashing function, because there's 2 things being mapped to the same number. I think there's there's another hash function that are also used like in cryptography, and for instance, we use when we learn how to do user authentication. And this is something that everyone does. Some we have to do ourselves, some we have to some service provides it for us. But we use a module called Bcrypt to hash passwords, and that is using a hashing function where it takes in a password in plain text. And at the end, it turns it into a sort of jumble mix of characters that are the hash representation of that password. And hashing functions for cryptography, they generally worry about one thing, which is from the hash, you shouldn't be able to go back to the original password. So yeah, if you a hashing function in the cryptography sense is a one-way function that you wouldn't be able to reverse. I feel like on our sense here, we're not caring about that. Yeah, and I guess like now that I'm thinking about knowing the hashing functions that we will use, we could from the hashing function we could go back to the original one. We wouldn't know exactly which one the original is, but we will be able to narrow what the key was to a certain number. But that's not the purpose of this. I think hash function. Let's take a quick read here at the Wikipedia page. So it turns out that this is exactly what we're going to do. I'm glad that I pulled this around because I have forgotten. And I hope fixed size will make sense to map data of arbitrary size to a fixed size values. Um, the values returned from a hash function we can call a hash value, a hash code, digest, or simply hashes. Um, and the values are used to index a fixed size table called a hash table. That's the one we're going to do. Use a hash function to index a hash table is called hashing or scatter storage addressing. This is also a good representation of what we're going to do. So it turns out that we're going to have an array, and we're going to have an array, and we're going to hash keys, and those keys will be mapped to an index of this array. So the output of the hash function, the hashes themselves or the hash codes, we're going to use as indices in this array that I'm talking about. And this is a good representation for that. This Zoom window is getting in the way. Cool. Okay. So let's go back here. So a hash function is just something that is going to let us map a specific piece of data to an integer. In this case, in this sense. So okay, so let's take a look at what a simple hashing function could look like. So this is a simple hashing function. What we will do is we'll take advantage of the fact that each character on a string has a UTF-16 code value. That is, so this connects back to the fact that computers only understand numbers. So when these letters, this F in my computer that is being displayed right now, is actually being in memory. It's actually a number. In memory, let's say UTF-16. There are a good number of them. Let's say table, an ASCII table or UTF-16 table. So there is a lot of them. F. Oh, there is a lot of Fs. Capital F is 70 in my computer, and in your computer as well. And in binary, that's this number. I think this is binary. Yeah. And lowercase f is 102. And this is in binary. So in memory, there are these bits that you have on or off, and that is representing this F in my computer. If you think about it, it's kind of crazy. That those ones and zeros create everything that we're seeing right now. So what the hashing function, what we will do, so we need that, basically we need to turn a string into an integer. And that's gonna be our hashing function. The way in which we'll do is we will loop over the key or the string in this case. We'll loop through that, adding up the codes of each one of the characters. So we're gonna use this function that we don't use as much. We're gonna do key character code at index I, and that's gonna give us the number representation of that character, and we're just gonna add that to a sum. We're gonna accumulate it into a sum. So I should start with VS Code here. Oops. Actually, I think Um, let's see review. Let's open this up. Create a new folder here. I'll push this code later. I'm gonna call this just index.js. Cool. So let's do our function. I'm gonna use S6, ES5, hash. We're gonna have an accumulator. Let sum equal 0, and we're gonna do let's loop with a more elegant loop. Let character. I always have to think about in. No, I think it's off. Key. Sum plus equal. Oh, now I see why they use the regular loop. Because this is doing the index here. So I want it to be fancy, and I can't. Let's do a regular loop. Oh, key char code I. So let's say that. So now we can hash things with this simple hashing function. We can say let's do console log hash. Let's hash Sally, for example. I'm also gonna hash my name because I don't know what that will be. And let's run this. No index.js. Well, I guess I have to go into the hash tables folder first. Cool. So Sally gave us 517. My name 491. Also, just to develop a sense for how this one works, char code add. As I said, let's say we have. I'm going to go in node here. Let's say we have. So we have full, right? So we have the string full. And does anyone remember what the code for f was, for lowercase f?
70.
Let's see. Char code 0. I think capital F was 70. Lowercase f is 102.
Yeah.
So if we look at back our table here, lowercase f is 102 in decimal. This in binary. So you see how this is saying character code at index 0. Index 0 of this string is f, and therefore we get 102. Right? So what we're doing is we're just looping over, adding all those numbers to get a numeric value. And if we think about it, I was going to refer back here. Fixed size value. Yeah, no, okay. So I think we still can't talk about the fixed size value. We'll get there. But here we're already doing this, which is we're mapping data from a string to a number. So we're able to do that. I wanted to see char code. Let's take a look at this function. Index string from I guess I wanted to see if I could use it in a different way. But no, I don't think I can do it easily. Code point from chart code. Yeah, that's to, this will be to do the opposite, which is from the character code into the actual character, from the number to the actual character. So you can see that this will produce this. These are actually independent characters. Cool. Okay, so that's the first part. So here we're just able to hash a string into a number. So let's say we wanted to have this in a hash table where we have names of people, and the value we were going to store their email. This is an example where we could use an object for, right? So here we come to a problem, at least with our hashing algorithm. The problem is, let's do Sally, Dean, Dane. And say Sally is mapping to this. It's mapping to this. Dane is a white hole is mapping to that.
Yeah, I think you just need the commas at the end of Dean Dane, and yeah.
Gotcha. So let's take a look. Oops, I went to that again. So here we have a problem. What's the problem that we're seeing here?
You have two similar or matching rather indexes, not indexes, but hashes.
That's right. So we have two different values, two different keys, Dean and Dane, that are mapping to the same value, 376. 376, that's right. That's because our hashing function, the only thing that is doing is looking at each character, and then looking at the character code and then adding them to the sum, right? But since the point of this is not the hashing function as a whole, it's more of the understanding of the hash table, not as much the hashing function. We're gonna work with this. We're gonna work with this hashing function. So this is known as a collision. A collision is when two different keys, map to the same value. They map to the same hash. I guess I should say, or the same hash code. And we're going to learn how to deal with that and how does hash tables deal with when that happens. Ideally, this wouldn't happen. This would be rare cases, and that's how like real hash tables work. Collisions actually happen very rarely because they're using better hashing functions. Cool. So that's a collision. So how would we solve that? The way in which we will solve that is when two things are mapping to the same hash. What we'll do is we will have, this is what this graph is about. We have our hashing function. Let's say we hash D, and that fell on this bucket here. And then we hash F, and that is also going to fall on this bucket here. What we will do is we will have it in our bucket, and we'll clarify what that means in a second. In our bucket, we'll have a linked list so that when two things map to the same bucket, so we're gonna be using this. We're gonna be using this these numbers as our sort of the address for our buckets. So when two things map to the same bucket, what we'll do is we'll link it using a linked list, where we keep the first thing that was inserted on the head node, and the node after that, if there's something that if there's another key that where we get a collision, we'll add it at the end. We'll link it to the end of our linked list. There. So that's how then we will have one attached to the other one in case two values D and F here map to the same bucket. And I feel like hopefully once we actually look at the implementation, this will make a bit more sense.
So it's just like assigning it to like a .next in case like they point to the same thing. That's really it. And in order, if you want to access that, you would just go to that bucket and then do like .next, and then you'll just be able to get that value.
That's right. But if that gets long, then if our linked list get too long, then that means that we have a really bad hashing function, which could happen with our current hashing function. Yeah. So here's like in our case, Dean and Dane would be at index 376 chained together using a linked list. So hopefully we can see that. Okay. Questions or thoughts up until now? I know it has been left a bunch of stuff to explain later, but hopefully that will be the implementation that clears some of that stuff. But any other questions?
When we're inserting new elements to our when there is a collision, you said it increases the time complexity.
Mm-hmm.
So are the things that are inserted, are they in order of insertion, or does that not even really matter?
That's a good point. In the linked list, it will be in the order of insertion. But nothing comes to mind about where that will be helpful, where that order of insertion. The linked list will keep its order of insertion because that's the way that linked lists work.
Yeah.
But I don't think it will be something that we take advantage of.
Oh, okay.
Yep. Cool. Okay, so we have our hashing function. It's always a bit tricky where to keep you guys and that I can see also the screen. Yeah, I think this is good. Okay, so we have our hashing function. So let's start implementing this. So what we will have, we're gonna write some methods. We're gonna walk through those. For the main methods that we're gonna have will be insert, get. Yeah, those are the main ones. So let's I'm gonna start writing here a class. So I'm gonna say class hash table structure, and then we're gonna keep literally we're just gonna have an array that we're gonna call buckets. That's it. And I'm also gonna need since we're gonna have a linked list as well, so I'm gonna need a linked list. So I'm just gonna have a node. I was thinking of having a linked list class with some methods to make it easier, but let's just have a node class. And these nodes for our linked list will keep track of 3 pieces of information. Also, there's a cool thing here where we sort of get fixated in a linked list, like it's just the value and next. But no, you can store anything you want. In this case, we're needing a node that keeps track of 3 things: the key, the value, and the next. So we'll do the same constructor. We're gonna receive a key, a value, and next can just be null, which is the default. I guess, yeah, this is fine. I don't need the next there. I think. Hold on, unless there's something that we're doing with that here, which I don't think we are. Node. No. So we have our node. We're gonna have this dot key equal to key. This dot value equal to value, and this dot next is equal to null. So we have a node for linked list there. Also, an idea of what Marvin was said initially came to mind, which I think we're gonna need actually. The size of the hash table. I think we're gonna need to have a size, an initial size, because of this is something that I didn't foresee happening. Yeah, because like now it's us that we're implementing it, and just like with anything that we're implementing, we don't get stuff for free, as like we get in an array that we didn't implement. It just grows as needed. So I'm actually going to need here a size. We're going to need a size there, because we need, I guess, if we don't pass a size here, what I could do, like what I, as the developer, this hash table could do, is say, okay, my hash tables by default are gonna be 100. They're gonna be capacity at 100. I'm gonna, maybe that's because like I could say, well, for the people that are gonna use this hash table, I know that their use case never needs more than 100 buckets. So then that will be totally fine. Let's pass a size here to make it a bit more dynamic in that sense. And now what I'm gonna do here is I'm gonna say also this dot size. Let's set the size here, and we're gonna allocate an array of that size, just like this. So we have an array of size whatever we want. So the functions that we're gonna have in the hash table are going to be, I'm gonna have a hash function that's gonna take the key, and this is actually gonna be our hash function. So let me just move this here. Our hash function. Wait, hold on. Give me 1 sec, because I think I came across something where the hash function. I think the hash function actually doesn't come. Is not part of the hash table. Let's do. Let me do a quick Google search. Hash function. For hash table. I think the hash table, the hash function is not part of the hash table itself. It's its own separate thing. Let's do hash function, hash table method. I kind of feel like there must be a Stack Overflow method. Let me just ask it like this. Get the sense that I'm not gonna get anything for that. Yeah. So I'm gonna err on the side that the hash function is actually not part of the hash table itself. Because I think so. For the 6.2 folks, Ben was the one who initially introduced us to hash tables when we were still in person, and I think I remember him leaving the hash function outside. So we're gonna have the hash function outside, because I think it is not actually part of the hash table. is something that it uses outside. And I also had, I also came across an old content where in Swift, it turns out that the elements themselves, so like the string or whatever it is that you want to hash, keeps track of its own hashing function there. So we're just going to have this function here outside hash. That's going to be the one that we use. So sorry about that. So here we're going to have the methods are insert. We're going to have get. This could be like we could name them anything. Get, and I think those are the main ones really. Let me see. Those are the ones we implement here. We could have delete. You could have keys that returns all the keys. We could have values that returns all the values. We could have clear to clear our hash table, etc. But these are the main ones. These are the ones that we want to focus on. Insert and get. Cool. Actually, let me just put them here. Hash delete or some of the ones that I would like to implement. Keys. Cool. And then, but we're really only going to implement these two. So insert needs to get a key, and get also needs to get a key. Okay, so let's think about insert. So in insert is where we're gonna take into account this map data of arbitrary size into fixed size values. This fixed size hopefully will make sense here. So the way in which we're going to do this is keeping with this example. Let me remove that. So we have our hash function, we have our hash table. The way in which we'll do this is I'm going to say let emails, or let's say fellow emails. And we're going to have, I'm going to say equal new hash table. And let's say we're going to have 30. Our hash table will be initially of size 30. And then I will do something like fellow emails that insert. I'm going to say Marvin, for example. And then I'm going to insert his emails, which is Marvin Thompson at pursuit.org. Because I didn't do that. Let's actually insert all of you. Douglas. Mackerel. Like that. I think I'm missing the A.
Yeah, that's fine. Thank you.
Cool. And we have Joanne. Inama. Oh, we had Maria. I don't know Maria's email. I think it's Maria Lisa.
Maria Martinez, but that's fine. Thank you.
Only Maria Martinez?
Yeah, but that's okay. Thank you.
Okay. And Siham. Bessie. Cool. So this is the way that we're gonna insert this. And that what we want is, yeah, we want a map well, we want to map so that whenever we want to find Marvin's email, the hash table returns us that immediately. Cool. So then insert is gonna take a key and also the value that we're gonna insert. Cool. So the way in which we're gonna do this is we need to hash the key first. So let's do let hash. I'm gonna say, what should I call this? Let's call it hash code equal hash key. And
Wait,
then
so Leo, sorry to cut you off. So we're hashing the key, or are we inserting an already hashed key?
So we are going to hash the key first to then map that key to an index in an array.
Okay, cool.
So I'm going to call this the hash code. I think we also and I'm going to have something called I'm going to have something called index. Not too sure about that name. Let me just see what we call it here. We call it bucket, but I think, yeah, this goes. I'm gonna call it bucket. I'm gonna call it bucket index. Middle ground there. And I think yeah, this the way in which this was implemented before, which was coming back to me when Ben delivered that lesson for us. So the bucket index. So we map the key to a hash code, and now we need to map that hash code to an index in our array, in our buckets. So what we're going to do is simple modulo operand. We're going to do hash code modulo this dot size. What this will do is, so you saw how like we have Sally 517. We cannot use this as an index directly because we don't have an index that's that big in an array of 30. So what we'll do is just that the modulo will make it map within the fixed size of our hash table, and then that will give us 7. Then 7 is the index that we'll use. So then we'll do that. Then what we will do after that, I'm thinking even before that, let's do this because I think this goes a bit fast over there. What if we could a naive implementation could just be this dot buckets add bucket index equal value. So here we are mapping our keys to indices in our array, and we can take a look at what that looks like that. If I do console log hello emails, and then I come to node index.js. This is what that looks like. I don't know if that's big enough. So we see that Maria Lisa was mapped to index 11. Joanne was mapped to index 11, 6 empty items, 17, I think. Wait, no, sorry, not index 11. I always keep 10 empty items. So Maria Lisa got mapped to index 10. And Joanne got mapped to index 16. Marvin got mapped to index 16, I guess 16 plus 3, 19. I'm off by 1, I think. Do we have all of you, or is there Douglas? Douglas is not here. So Douglas is not here. Now this is the point that I wanted to make. Douglas is not here because some other hash, some other key hashed to the same bucket, and it was overwritten. So that was a collision there. We don't know which one it was, unless we console log, like maybe we console log here, see where Douglas was. Douglas made it to index, oh wait, this is interesting. So I guess it was 21 empty items. So this is index 21. 787. So this is index 28. 28. So I think CHAMS collided with Douglas there. Let's do this. Fell index 28, which was what I think. Oh, here I'm breaking a bit the rules of the hash table, going into the array itself to check what we have there. But this is just for experimenting. So you see, I'm always off by 1. It's either, oops, hold on. Wait, maybe I didn't do my math correctly. 21 empty items. So this is index 21. Let me just double check that. I think Marvin is being mapped to index 21. That's right. Okay, we got Marvin at index 21. So 21 plus 7 is 28. I have put 28 there. So is it then 29? 29. So Douglas is being mapped to index 29. And I think CHAM is also being mapped to index 29. There we go. So this so happens that CHAMS as a name mapped to some number that then when we module that to the size of our table, happen to give us the same index, and then we have a collision. Let me stop there. I guess, like, before even doing this ugly thing, which was looking at the array, what I should have done is let's quickly implement get with this simple scheme of things. So we just need to do this process exactly the same. I'm gonna hash code. Let's hash the key that you have, and then that bucket index. We do the hash code, modulo the size of the hash table, and we do this dot buckets bucket index. We return this. So now we have a simple insert and get functionality. So this is a hash table already. It's just a somewhat poor one because it's not even handling collisions. Like, but this is already a hash table. Actually, instead of opening this here, let me open my separate terminal. This was pursuit DSA video, so that I can have this here.
may be jumping ahead like 8 steps, but if we increase the size, do we have to rehash absolutely everything that's in the hash map? Or can we get away with just tacking on some extra space at the end?
You'll have to rehash all the keys, yeah. Because if not, you will have a not very distributed hash table. And also, well, not only that, actually, I don't think that's the main point. The main point is that we were using, if we just add slots, we were using the size to derive the bucket index. Then that will make it so that we're going to get a different number if we suddenly have more space. There's no node index hash tables, which is what we are. Node index, yes. So instead of doing this, what I should have done now here is I can do fellows that get, and then I can put Douglas here. And here, actually, let me do this here. Or let's get Marvin. So, oops, I keep opening that. Let's run this here. So now we see here that by a key, now I was able to get the value. Given the Marvin key, I was able to get the value that I was storing under that key, which was his email. Cool. And we can forget a little bit about the indices. But the point is, let me stop here. Any questions or thoughts up until this point? I notice I have been a bit all over the place.
So this currently still isn't handling collisions, right? This is still like not accounting for this, or
this is not accounting for collisions at all. Like for instance, this is not a good hash table because from the hash table, you will just have data disappearing, like Douglas disappear internally. Yeah.
Okay.
But I feel like the point is like now is like that all hash tables, JavaScript objects, all of that under the hood is an array. And this is the process how we are mapping a string to a number that then we use as the index in this array. Any hash table, any dictionary, any programming language is still doing a version of this. Okay, so this is not handling collisions. For example, look at this. Look at how it's handling collisions so badly that if we inserted 5 of you here, and after I'm going to get Douglas, I get Siham. I got Siham because Douglas happens to, with my hashing function, map to the same thing that Siham mapped to. So then this could be a very confusing hash table to use in a programming question, for example. But does this make sense? I want to stop here for a second. Just give me a thumbs up if you have a feeling that it works for you, and maybe some other reaction if you don't feel too comfortable. Since we're a few, I guess I want to just check. I think I saw 2 thumbs up. Joanne, how do you feel about it? Or Maria Lisa or Siham?
I'm just a little confused. Well, I guess not necessarily confused, but like, why is CM and Douglas overlapping? Because in the other example we saw, Dean and Dean had the same exact characters, right? But Douglas and CM, they don't have the same characters.
That's a good question. Yes. Yeah. So Dean and Dane overlapped. They gave us the exact same count. So that one makes sense there. But then here, Douglas and Sihan, they don't have the same characters. Why are they still, colliding? Right? The reason is because of the fixed size here. The fixed size. So just to get a better sense of that, let's console log here because we are implementing this and then we can do whatever we want. So let's console log here. Can I console log the key, the hash code, and the bucket index. So we can see what's going on there. And then I'm gonna comment out this. So just the insertions are happening. So we run this.
Yeah,
Oops.
you can put console log.
Oh, thank you. Console log. Console is not a function. So let's take a look at this. So Marvin's hash code is 621. That's what the letters, the characters on his name add up to, and the bucket. So when we do 621, that is a number that's larger than the buckets that we have, which at the moment is 30, right? So we want to constrain that to that fixed size of 30. So we modulo by 30. We modulo 621 by 30, and then we get 21. 21 is within that 30 buckets that we have, right? Douglas code is 719, and modulo 30, that's going to give us 29. And Ziham, even though look at her hash code, her hash code is 599. It just so happened that 599 modulo 30 also maps to 29. And then there's where we have the collision. I guess this is a mathy part that I don't fully understand. Because if we have someone, let's say, that has a letter different than Siham, say F, next letter after E, for some reason. This is an imaginary fellow. Oops. Node index.js. We see that Siham with an F at the end, with an F, will map to the next hash code here. Wait, yeah. But then we see that when we do that modulo 30, we get 0. So the reason why Douglas and Siham were mapped to the same index is because of the constrained size that we have of our array, where we want numbers to fit in this 30 buckets. So we need to do the modulo 30, or the modulo, in this case, not modulo 30, just modulo the size of the hash table. Does that add a little bit, Joanne, to what you were saying? Does that aid there a little bit? The fact that we want to make 719 fit in 30 available slots. A very simple way to do that is then modulo by the number of slots that you have. And it just happened to be that even though they have different hash codes, when we make them fit in these 30 buckets, in one of these 30 buckets, they both gave the same index. And then that's why Douglas is being overwritten, because Douglas gets bucket 29 first, and then Siham gets bucket 29 after. and erases Douglas. How does that aid in anything?
A little bit.
Okay. Yeah, I feel like I'm not doing a good job at, or I'm not being able to express it better. The fact that I guess like, you can have any number. You can have, give me one number, a large number, any number. Join.
100,000. Yes.
100,000. Okay, this is 100,000. So, if I want to, if I want to have, how could I explain this? I guess like what I was gonna say, if I want to say, let's say we have 100,000, but I want to, um, um, I was gonna say I want to make it fit in in 30 buckets. What I could do here is just do modulo 30, and that gives me, oh, that gives me 10 in this case. So from this number, I was able to, if I want to make, that's not a good way of explaining it, but if I want, if I have this large number and I want to sort of wrap it around and make it fit into one of 30 slots, what I could do is modulo 30, and that gives me one number that is between 1 and 30. Yeah, I feel like I'm unable to go any deeper there. So the idea is that we derive a hash code from the key. That hash code can be any number, but we still need that number to be within the buckets that we currently have. So to wrap it around, we do modulo the size of the, or how many buckets you have, so that that hash code can be mapped to one of the buckets that we have. So here, here we have this very naive implementation where we are just calculating the hash code, calculating the index by wrapping the hash code with, by modulating the hash code by the size. Oh, you know what? Maybe this could help. Modulo definition. Let's see. An independent self-contained unit of space, grab any of a number of distinct but units for which a program may be built up. No. Modulo operator. Yeah, I mean, this is the definition that determines the remainder. I guess, I mean, that's what we're taking advantage of. In this example, the remainder of dividing 10,000 by 30 is 10. But that also, yeah, no, I think this just gets into some other mathy thing that I'm just not sure. Use cases. even or alternating. Oh, this is the use case that we're using it for. So the modulo operator to restrict to a number range. This is exactly what we want. So here the hash code will give us any number, but we need to restrict it to one of 0 to 29 because that's the number of buckets we have. We have 30. So we want to restrict this number to that range. We want to restrict the hash code to the range 0 to 29, which are the 30 buckets that we have. So when you're using the modules operators for even or alternation, you're actually taking advantage of one of its more helpful properties, though you might not realize it. Here's the property. The range of x modulo n is between 0 and n minus 1, which is to say that the modulo operation will not return more than the divisor. Again, examples of that might help to clarify this idea. Divisor 5, the results will be in range 0 from 4. So yeah, this is what we're doing. Any number modulo 5 will give you a number that is in the range 1, 0 to 4, and so on and so forth. Yeah. So like 218, still modulo 5 is still going to give us 3. It was going to give us, so this is the way in which we're using it here. We want to restrict that hash code to be in the range of the available buckets. Does that add any context?
Yeah. So I was trying to do some math to that,
Yep.
especially with well, at least with what Douglas got, and we did get 29 for that. Because at first I was thinking maybe it was random, but it's
I
not.
see. It's not random, yeah. So what we're doing here is we're constraining these numbers because these numbers can be, yeah, and these numbers can be of arbitrary size, right? It can be anything, but we're constraining them to a limited, a fixed size. This is exactly what the Wikipedia article says here. Use to map data of arbitrary size to fixed size values, right? So our key can be anything and it will be very large, and we are keeping it within the range using the modulo operator. So in other words, like if I go back here, we get the hash code for range 621, and we want to keep that within the range 0 to 29. So we do modulo 30, and that gives us 21, and so on and so forth. And then that's why it just happened to be that when we divide 719 by 30, the remainder is 29, and when we divide 599 by 30, the remainder is also 29. The remainder. That's another word that I have issues with. Reminder and remainder. Okay. Any other thoughts or questions on this? Okay, so then let's think about how to handle collisions then. So we realize here that there's a collision between the key Douglas and the key C-Ham. And the current way in which our hash table is handling collisions is by just overriding the previous value. So in other words, it's not handling the collision at all. So the way in which we will handle that is, as we said in our lesson, using a linked list. So when some key maps to the same value, we're just gonna add, and there is a value already there, we're gonna add that to a linked list. So to do that, to begin with, then we should have our values stored at our indices should not be just the straight value. It should be a node for a linked list that we're gonna have. So I'm gonna do let let's do here. Let new node equal new node. Actually, I'm just gonna call this node, and we're gonna call the key to create a node. Is it? We've passed the key and the value, so we're gonna pass the key and the value for that node, and we're gonna set our node there. We're gonna set our node there. So instead of putting the value straight into it, what we now have is a nodes. So if we look at the hash table right now, by console logging it, fellow emails. If I quit from here. We see that now is not the email straight in the array, is actually a node for each one of you. And we see that, well, Siham's node, because it was going to be mapped to the same index than Douglas, overwrote Douglas's node. So hopefully we can fix that so we don't leave Douglas out of our hash table. Cool. So the way then we should do that is through chaining this linked list. Oh, we should also fix. Well, we'll come back to fixing our this one as we have a linked list. So now we have a node. So what we should do is we should check. We should check if that bucket is already used up. So if something already mapped to that value. So we're gonna do if that buckets at that bucket, then that means that there was something that already mapped there. In that case, well, let's take care of the opposite case, which is when there is nothing there, when nothing has been mapped. What we want to do is just set the node. So we do this dot buckets add that bucket index equal node. So if the bucket is empty, if it is available, then we just set the node there. If it's not available, then that means that we have a collision. That's the case where we had a collision, which is what we're currently experiencing with Douglas and Siham. So if that's the case, then I don't remember the way in which we did it here. Let me check here really quickly. Insert, okay. So here we are inserting at the end. Oh, I guess I'm skipping a few cases here. Let me have that open. So the first case, yeah, this is the same. It's the same thing. If this is the case, then what we want to do. Wait, hold on. I guess I should just go more by what we currently have here. So this is saying if we don't have a bucket, or if the bucket is available, let's just add a new node there. Yeah, this is just a better way of putting it. If let's do that here. If we don't have this buckets at bucket index, then that means that the bucket is available. We can just put the new node there. Otherwise, if the node if it's not available, but the keys match at that bucket index triple equals the key that is coming in, that means that we're overriding the value of that. That means that we're overriding the value of that node, which then we can just do buckets bucket index that value equal the new value. That's the second case. Otherwise, else, wait, do we have, oh, these are an else if. Else if. Else. Otherwise, that means that then it's a collision, is the collision case. Where in that case, what this is doing is just iterating over the linked list until we no longer have a next, and then add the element all the way at the end. So we could just do that. Let's say let current node equal to the first node, which is this dot buckets at the bucket index. And while we could just do current node dot next, if current node that next dot key is equal to the key, that means we're overriding one. That means we're overriding one of the nodes there. Then that means we do current node. I think I have to disable that. This autocomplete help. It gets in the way a little bit. Next dot value equal to value. And then we return here to quit from the while loop. To keep the while loop going, we set current node equal to current node dot next. Also, I think I have a spelling mistake here. Current node equal current node dot next. If we never fell into this scenario, then that means that we are reached the end of the linked list, and we can just do, say, the current node that next is equal to the node that we created, which is this one here. Okay, so let's think about this. This is quite a bit here. So we're saying if the bucket is available, well, let me start from the beginning. To insert, we have a key and a value. We hash the key, we get a hash code. We limit that hash code to the bucket size, so, to our hash table size, I should say, by saying hash code modulo the size of our hash table. And then we have a hash code and a bucket index that we can use. After that, we create a new node with the key and the value of our of the thing that we want to insert, and then we check if the bucket is available. If there's nothing in that bucket yet, we're just fine adding the node straight there. However, if what you're inserting, or if there's something already there, if there's something already there in that bucket, then we check if that thing has the same key than the key you are trying to insert. If the keys are the same, wait, I'm missing here an important bit, key. If the keys are the same, then that means you want to overwrite what was there before with something new, which then that means, okay, buckets, whatever is at that bucket, that value will be overwritten with the new value that's coming in. If that is not any of the other cases, then that means that was the case where we hit a collision, and we want to then loop over the linked list that we had, and we just set sort of a current node here to be updated, sort of our pointer, to be the first node of our buckets. And then we just say, as long as we have a next on the current node, let's check if the current node next key matches the key that's coming in. If so, then that means that we were overriding value for one of the elements that was stored in one of the nodes. So we can just override that with current node dot next, that value equal to the new value. And then we return to quit from the while loop. If that key is a key that we haven't seen before, if it's a brand new key, then and as you know, we go iterating over the linked list by just resetting current node to current node dot next. If it's a key that we never saw, that we haven't seen before, that haven't been inserted before, but it just happened to map to the same bucket that an earlier key did, then we just finish for the while loop to get to the end of the linked list. And once we have gotten to the end, we can just say current node that next equal the new node that we created with the new key. So if we have this right now, we should be able to see then that Douglas should be preserved. Douglas should be preserved in our hash table. We can't get it yet, but it should be preserved. Let's take a look. So I'm still gonna console log the entire thing. And then let's run it here. So node index.js. Okay, and then we have Maria, Joanne, Marvin. We see Douglas. Douglas was not overwritten, which is good. And then we see that the next of that is a node. That next node is the ham. It's just that console log gives up after a certain depth, and it doesn't go to print that one out. But that new node, the fact that it doesn't say null or it doesn't say anything else, that new node, that node there is CHAM node. So what happened there was Marvin got inserted, Marvin's slot was available, and then the node just got put there. Then Douglas was inserted. When Douglas was first inserted, the slot was available. It was just put there. Joanne was inserted, the slot where that map to was available, so it was just put there, and same for Maria. When Siham was to be inserted, if we follow this here, the hash code, we got a new hash code. Siham is 599. The bucket index is 29, which is the same bucket index than Douglas. So then we don't go here because that slot is not available. We are not updating Douglas because this key is different. Siham's key is different from Douglas's key. So then that means that we must have had a collision that two keys map to the same one, to the same index. And then we grab the current node. The current node will be Douglas's node. And then we say while current node dot next. In fact, when Douglas was first inserted, Douglas doesn't have a next node. So then we just fall out of this for loop and we just go straight here. Current node dot next, which is Douglas dot next equal new node, and that new node was Siham's node that was created here. Questions or thoughts on this part? The insert and the linked list. Okay, I think I saw some thumbs up. Any part here that might feel be confusing still? Anyone? So the idea is to visualize this a bit better. Oh, to visualize this a bit better, let me see if I can try to do that here. Let's say we have well, I'm not sure if that'll be very successful, but let's try it out. So we have 30 slots, and this is our array. And imagine that we have 30 slots. We saw that Douglas's node was mapped to index 29, so that's like the very end here. Let's say Douglas. That circle is a small node. I think Maria was mapped to the top, somewhere to the top. If I go back here, yeah, Maria is there, Joanne, and then Marvin. So Maria is around here. Joanne is somewhere around here. Marvin was somewhere around here. And then there's slots in between, right? There's like 10 slots for Maria, and then those are the nodes. When we're and I think Maria we said was, this is index 10. Joanne is 10 and 16, so Joanne is 17. Oh, I guess I have them here, don't I? Yeah, 17. Then Marvin is 21 and Douglas is 29. So when we want to insert CM, we hash that. We hash that, and it gives us 29 as well. So that means that CM will map here, but we don't want to overwrite Douglas. So what we do is, because that's the point of why we make this linked list or nodes that we can then connect, because then I can say, okay, if bucket 29 is already occupied, let's check if CM, which is the key, matches the node that we have there. No, it doesn't match it doesn't match the key in the node, which is Douglas. So then that means that they're different. They're different keys. They're different elements. So in that case, then let's loop over this linked list, which in this case is just length 1. And once we reach the end of the linked list, which is the node itself, we just create a new node with CHAM. We create a new node with CHAM in it, and then we say, okay, the current node at next, which is Douglas, is going to equal to the new node, and then we have this. And if there, let's just imagine that Alejo mapped to 29 as well for some reason, then the same process happens again, which is we check if we check the first node, see if the keys are the same. The key is Alejo, and then the key of this node is Douglas. They're not the same. So then that means we need to loop over to check if any of the nodes in this linked list is Alejo, because if it's Alejo, then that means that we want to overwrite the value. Well, I just realized that, you know, I put the keys, but I didn't put the values, which is the email. The emails are actually the values. The keys are just your names. So if Alejo map there, what we'll need to do is just iterate over to see if there is any node with that key of Alejo. If there is, then that means we're just overriding the value. In this case, there is not. So that means we need to go through the end of the list. We create a new node with the key and the value inside. And then we say the last node that next is going to be equal to Alejo, like that. Does this make sense, at least at a conceptual level?
It does, yeah.
Cool.
So I guess when you're searching to get, we now have to also account for encountering a linked list that has multiple nexts and then iterate through those, I guess.
That's exactly right. Mm-hmm. So let's do that. Let's do that next. But also, so whenever you, again, this is more of a thought exercise that we're doing here, for understanding how these things work. There is, I think, there is something called, I don't know if we talked about it in the lesson. No. Where did I see that? I think it was in an old I think I was looking at our old curriculum when I was a fellow. This was the curriculum. DSA. Wait, no. Where? I think it might have been. No, yeah, I can't find it. But the point is that when you see that your hash table is starting to have a very long linked list, then that means that you're having a lot of collisions, which means you should do something about it, because your time complexity to insert and get is gonna just keep worsening, right? We want our time complexity to stay at constant time. Maybe looping 1 or 2 times is not a bad thing if we have, you know, this. But if my linked list is starting to grow to maybe you know, I guess for the size of this hash table, if we have a longer linked list, then that means that maybe our hash function is not a very good one, and we should then try to figure out how to solve that. Either what we could do that is, in the way in which you could do that is by using a better hashing function, or by increasing the size of our buckets, by increasing the size of our array. So one thing that just came to mind here is known how so I hope I have mentioned this a few times, where in DSA and programming, and what we do, we're always doing this trade between time and space, right? So you save time by using more space, or vice versa, you save space by using more time. So the classic example is what's a good example of that? Let's say finding duplicates in an array, right? We can find duplicates in an array in quadratic time. If we have nested loops, we compare each number to every other number, right? So that's quadratic time. And constant space, we're not using anything additionally. But if we want to gain in time, we can use more space. So if we have a hash table, if we have an object that's keeping track of the numbers we have seen so far, then we could find duplicate numbers in linear time. So the point is that we're always doing this trade-off of time for space, space for time. And this applies to hash tables here, because right now we have 30 slots, of which only 5 are being used, but we're able to get elements in constant time, right? But we have 30 slots ready to go. Well, I guess 25. In this case, wait, how many exactly? 4. We're using 4 slots in this case because CM and Douglas are colliding. We're using four slots. But the point is that there is a lot of wasted space if you think about it. Like there is a bunch of other stuff that is empty, but we get the constant time. We get the constant time operation, the constant time lookup. So to get is just is actually very similar to this. Is very similar to that. So what we'll do is the same. We'll do well. Let's do this. If this dot buckets, if this dot buckets bucket index is not there, just return undefined. Else if this dot buckets, I kind of feel like I keep doing this. What if I say let current node equal if I say if not current node, then return, oops, return undefined. If current node that key is equal to the key of what we're trying to get, then return, maybe we could do it here. Return current node that value. Else we need to iterate, right? Else we're gonna say while current node next, same thing, if current node next that key equal the key that we're searching for, then that means we can return current node that value. Else, else we just keep increasing current node, or keep moving that pointer. Current node is equal to current node that next node that next, and at the end of the loop, then we will know that we can return current node. Oh, actually, this is interesting. No, here we'll, at the end, we could just say, we don't need to say anything there. If we didn't find it, let's just return undefined. I guess like we could get rid of this if statement. Because that's also going to be here. If we couldn't find it after that, after looping over, we just return undefined. Return undefined. Let's do it like this. Let's get rid of this case. Oh, wait, hold on. No. I can't get rid of this because current node.next of undefined doesn't exist. So this is fine. So first we check if there is something there. If there is nothing there, then we just return undefined. Else, if the first node that we were looking for, the key happens to match the key that we're searching for, then we just return that current node that value. Otherwise, we search through the linked list, and where we see a match in the key, then we return that current value, that node value. Otherwise, we keep searching. If we finish that and we didn't find anything, we just return undefined. So let's check this out. Let's see if this works. Let's do fellows emails that get Douglas. See what we get here. Just put up the code. So because we're mapping names to emails, we got the value, right? We got Douglas's email. Now let's get Cham. See if we have Cham. Also, hold on. Before we do that, let me console log. Let me stop console logging here. So we already put that down. So let's try to run this again. Oh no, we still have something going on here. Cham return Douglas' email. There is a bug on my hash table. We should have gotten Cham's email. Let's think about this. So that must be in my get. Well, I guess that could be in my insert too. Let's take a look at the get first. So we hash, then we did current node. If current node matches the key, then return current node that value. And the first node, it shouldn't match because the key will be Douglas, and the key we're searching for is Cham. So just to check, let's do a console log here for current node that key and key, see what we get. Okay, so we see that Douglas and Cham. So current node key is Douglas, and the key we're searching for is Cham. Cool. So then let me actually put that, I guess, here. Oh, here's did anybody catch where the error is? The error is in this line.
Should it return current node.next.key versus current node.value?
That's exactly right.
Ah, there we go.
Because the key are matching on the next, but I was returning the current, so the previous one now. So there we go. That there. Now we see we get Douglas's email and we get Cham's email in our hash table. And we now now know, because of the inspection that we did, that those two are it's a collision there. But then in this way, you can insert in constant time if there is no collisions, which is the most common case. Is a good hashing function that avoids collisions well. No hashing function is perfect. I should say that. No hashing function is perfect, but there's better ways of hashing than the one that we're currently doing here. And since, again, the point of this is sort of more of the on understanding hash tables as a whole. We're now going to look at more complicated hashing functions. But in this way, then we are inserting constant time most of the times. Occasional when there's a collision, that will be that is if we go back to my thing here. Here, this is when I said the read or lookup will be constant if there is no collisions, or O of n, but important to distinguish what n is here, where n is the number of elements that were mapped to the same index, not where n is the number of elements in the hash table, where n is the number of collisions that we might have had in that case. And then find is wait, no. Okay, yeah, find we haven't implemented find, but we could do easily. Find will be O of n because find or searching through our entire hash table will require us to traverse the hash table, and if there is a linked list, then we need to traverse that linked list. So in the worst case, where we have to traverse the entire hash table, and we have a hash table that has a lot of collisions, then that will be O of n, where n is the number of elements in the hash table, and m, where m is the number of elements that are already mapped to the given hash. Cool. Updating, we already saw that insert is already doing updating at the same time. So maybe a better name for insert will be set instead of insert. But questions or thoughts on this?
While it's this is a very specific use case that we've created this very simple hash map for, would it be best to limit to when we're building our ad? I forgot from, so I can't remember what we called it. That we want to increase the size of the hash map if it collides more than 3 times, kind of thing, or what would be a good use case to increase this? When would we want to increase the size?
Mm-hmm. Yeah, the short answer for that is when you're starting to have very long linked list, and you could set that limit. Like you could say, well, I don't want my linked list to be more than 3. If I have maybe 2, 3 linked lists that are more than 3, then I want to double my capacity of my hash table. And that's really the way that they work. I think they call it hash table load factor, which is gonna tell you, yeah, load factor and rehashing. Let's take a look at this, see what we get. For insertion of key k and value v, pairing to a hash map, 2 steps are required. K is converted into a small integer, call a hash code. That's what we did using the hash function. The hash code is used to find an index. The hash code, modulo the array size, and entire linked list, and the entire linked list at that index. This is the chain that we're doing. Is search for the presence of k for k already. If found, the value is updated, and if not, kv pair is stored in a new node in the linked list. We did that. So load factor, complexity and load factor. This is actually an interesting read. For the first step, time taken depends on the key, on the key, on the hash function. For example, if the key is a string ABCD, then its hash function might depend on the length of the string. But for very larger values of n, the number of entries in the map, length of the keys is almost negligible in comparison to n. So hash computation can be considered to take place in constant time. This is to say, like, the hash, our hash function here has a complexity of n, where n is the length of the key. But the length of the key is generally negligible with the size of our hash table. Or like they're just two separate things. So the hashing time complexity depend on the length of the key, not really on the number of elements you have in the hash table. So that we can consider that just of n of one. Let's keep reading. So for the second step, the traversal of the list present at that index needs to be done. For this, the worst case may be that all the n entries are at the same index. So this will be a very long, a very small hash table with a lot of collections and a very long linked list in one of them. So time complexity will be O of n. But enough research has been done to make hash functions uniformly distribute the keys in the array. So this almost never happens. This is for, hash functions, the objects that you're creating, the stuff that's under the hood. But it's still on the same principles that we saw here today. So on average, if there are n entries and b is the size of the array, there would be n divided by 2 entries, n divided by b entries on each index. Let's think about that. If we have, I guess if we have 30, I guess a simple example would be if we have, like, let's say we have in our humble hash table, which maybe I was thinking that we could test it out a bit intensely, but if in our humble hash table we have 300 elements, right? And we only have 10 buckets, so that's our B, that's our array size. Then the average will be 30. The average will be 10 key value pairs per bucket, right? In our linked list, our linked list will be length 30. Sorry, 10. The value of n the number of elements divided by the size is called the load factor. That represents the load that there is in our map. So this is sort of what we could do then to Douglas's question is just watch this number. These load factors need to be kept low, which is sort of what we already talked, like no too long linked list. So that number of entries at one index is less, and so is the complexity almost constant. We want constant most of the time. So rehashing, this is something you alluded to as well, also Douglas. This is what I was thinking about, the rehashing when the load factor gets over 0.75. As the name suggests, rehashing means rehashing again. Basically, when the load factor increases to more than its predefined value, default value of a load factor is 0.75. The complexity increases. So to overcome this, the size of the array is increased. It could be double, for example. On all values are rehashed again and stored into the new double size array to maintain low load factor, and low complexity. Why rehashing? Rehashing is done because whenever the key value pairs are inserted into the map, the load factor increases, which implies that the time complexity also increases, as explained above. This might not give the required time complexity of O of 1. Hence, rehash must be done, increases the size of the bucket array so as to reduce the load factor and the time complexity. Now, also like here is like the calculation of the bucket depends on the size of the array directly in that modulo operation we're doing. I think this is interesting. Let's take a look at the way in which they did the hashing. Say insert. Oh, they use get bucket index. Oh, this is interesting. So this is in Java. It turns out that in Java, this is something I didn't know. In Java, things have something called a hash code, which you can do if this key is a string, you just do string that hash code, and that's going to give you a number already, and that number just get modulo the number of buckets that you have, the size of your array, and that gets used. Wait, I'm interested in hash code Java. Let's take a look at this. Oh, maybe here. This is the class object hash code, returns an integer, returns a hash code value for the object. This method is supported for the benefit of hash tables such as those provided by HashMap. HashMap seems to be something on the standard library of Java. Java has a standard library that includes a hash map. The general contract of hash code is whenever it is invoked on the same object more than once during an execution of a Java application, the hash code method must consistently return the same integer, provided no information used in equals comparison or the object is modified. This integer needs to remain consistent from one execution of an application to another execution of the same application. If two objects are equal according to the equals, maybe this is a function method, then calling hash code method on each of the two objects must produce the same integer result. It is not required that if two objects are unequal according to the equals Java line object method, then calling hash code method on each of those two objects must produce distinct integer results. However, the programmer should be aware that producing distinct integer results for unequal objects might improve the performance of hash tables. I guess I don't really understand this part. For unequal objects may improve the performance of hash tables. As much as reasonably practical, the hash code method defined by class object does return distinct integers for distinct objects. This is typically implemented by converting the internal address of the object into an integer. Oh, but this implementation technique is not required by the Java programming language, I guess the official one. So this is kind of interesting. And it's something that I suspected, but this is the first time I see it actually in writing. That the hashing code, a better type of hashing, takes into consideration the internal address of the object. That is the address at which that object is stored. So even if you have two objects that have the same values, they exist in two different places in memory, they could still have two different hashes. Yeah, this is the equals, but let's not go into there. So it looks here that hash code is a function, at least in Java, not in JavaScript, that we can call on objects themselves and even in strings to get the hash code. And then we can just do what we did, which is limit that to a range, modulating by our bucket, number of buckets. Okay, so then from here, I feel like that was a lot, but I hope it was a bit insightful. They recommend the load factor, you should try to keep it at 0.75. That means your buckets should be, your array of buckets should be 75% used. If it ever goes beyond that, then that means that you should probably rehash and double the size to keep that load factor low and therefore time complexity low on accessing and inserting. Cool. Questions or thoughts?
I didn't mean to sidetrack us, but that was really interesting. Thank you so much.
Of course. No worries. I'm really good at going off of the tracks when things get interesting. But any other questions, thoughts, Joanne, Maria?
I was afraid of hash tables before, but I'm not anymore. Thank you.
That is a very good compliment. I appreciate it. Yeah.
Thank you.
Yeah. So what happens when you do? So this is a hash table, right? But what happens when you do let's object equal this? Like under the hood, a hash table is being created that has an array somewhere that we can't see, but it is being created. And when we do object that name equal Maria, this is sort of syntactical sugar for saying insert into that hash table name with Maria, basically, and so on and so forth. So this is literally syntactic sugar for that insert operation. Cool. And same for getting. Okay. So other questions, thoughts? Do we want to do like an exercise that I'd like you to encourage you will be implement the hash method, which is it's the same as the get, but it should return a true or false if there is. This delete, it will be interesting because then you need to remove the node from if it's in the linked list, or remove the bucket, remove the element from the bucket itself. Keys will be interesting, for example, because keys, you should return all the keys. So then that means you need to loop over, the array, and get all the keys from all the nodes. And if anyone is a linked list that has some length, that has some nodes in, then you need to go there and capture those keys as well, to return. And that's all, so when we do something like this, name, let's say Maria, class, let's say 6.4, let's say car. I don't know if you drive, but I'm going to say you drive. You have a Corvette. And then when we do, you might have done this object that keys object. I guess I should say this is a person to be a bit more accurate. Corvette. And when we console log this, we see an array with all the keys. Under the hood, what happened was what I just described. That traversal over the elements in the hash table, which in this case are like these key value pairs. And then if the bucket is empty, then we don't do anything. If the bucket is not empty, then if there is a linked list, we traverse that linked list and we are keeping track of all the keys in our in that linked list, and we add them to an array, and then we return this part here. So I guess like here is, the way in which we did this here, if we were doing that with our hash table, it will be let person 2, or maybe same person, new class table. Or I guess in this case, there are some details that are being taken care of for us. For example, when you create an object like this, JavaScript maybe somehow, what I'm thinking, JavaScript as an interpreted language. But when we do something like this, I don't know exactly what is going on, but maybe a hash table gets created that is not too big. So it turns out that JavaScript, because it's an interpreted language, which what that means is that you could think of it, there's something that reads all your JavaScript first, parses it before it executes it. In that parsing, JavaScript is smart and see what is happening to person, for example. If person is person like receiving a ton of other keys later down in the program, or is person ever being removed keys from, and stuff like that. Then based on that, it could decide on how big of the underlying array should use to store it. But let's say here we'll just say 10, and then we can just say same person that insert name Maria. Oh, I'm missing. It's in a quote. Class 6.4 Corvette for a car. And then here we have like the same representation of a person. One, you could think of this is the native JavaScript version of it, and this is our own implemented hash table. But under the hood, the same stuff should be going on, and some other complications that make it more efficient. That is beyond the scope of this lesson and beyond what we need to know to be junior software engineers in this industry. Cool. So I think that's all I wanted to cover, unless there's anything else anyone wants to bring up.
Just want to thank you again for like doing this for us tonight. This was good. Thank you so much.
Cool. Yeah, you're welcome.
Thanks, Alejo. It was a really good refresher.
Awesome. I'm glad that it was helpful. And one more time, like this is not super practical in the sense that you're not gonna be doing this like on your day-to-day. But I think if it serves as, you know, as I think what Maria said, just being aware of it and stop being scared by any data structure. I think that is the goal that I didn't realize I had, but it was part of it. So cool. No, thank you for coming. Thank you for staying. And as always, feel free to reach out as you're working through stuff. I'm still available. I think I need to look at my calendar. But if there's anything anyone is working on, I'm still be on for like a half an hour. So let me know. I'll push this code. I'll make this recording available on YouTube so that if you ever want to rewatch it, or for folk that didn't come today, might have it there. Let's see. Yeah, I think that's all. I have the sense that there was one point that I wanted to make last, but it's escaping me right now. I think it was around the time complexities of one across the board. No, yeah. I don't think it was then that important. We covered most of it. Cool. All right, everyone. I hope you have a good night. Let me know if I can help in anything you're working on, and I'll see you next time.
Actually, before we close,
Yep.
Was it computed variables? No, computed something.
Oh.
When you are assigning the name to a I was trying to remember the name of the vocabulary word of what it was
A
from that
computed-
problem I had way back when I was inserting like through a variable. So I wanted to use a variable as the name of a key.
Mhm.
Maybe that is a computed variable. Was that what it
It's
was?
a computed property or a
Property.
computed key.
Thank you. Yeah.
Like this, I guess. Key employed.
Hmm.
So this is a computer property where we're adding, if we run this, we see that person, which is Maria, has 4 keys: name, class, car, and employed. And employed is going to hold true. And yeah, we have the actual keys inside of this variable called key. And we want to compute the value of that variable to go into person and add it. Cool.
Thank you.
All right. That is all. As I said, I hope everyone has a good night. We'll see you next time. Bye.
Thanks,
Good
everyone.
Good night.
Yeah.
Mhm.